What if I told you that everything you see around you, the stars, the planets, even the screen you're staring at right now, was once compressed into a space smaller than a single atom? It sounds like science fiction, but this is the mind-bending reality of the Big Bang, the event that set the entire universe into motion. For centuries, humans have looked up at the night sky and wondered, where did it all come from? Today, we're diving into the ultimate mystery of existence, the Big Bang. This isn't just a story about the birth of the cosmos. It's the key to understanding how galaxies formed, how stars ignited, and how life itself became possible. But here's the thing, the Big Bang isn't just a single moment in time. It's a puzzle filled with questions that still baffle scientists. What sparked the birth of the universe? How did everything we know emerge from what seems like nothing? And what does it all mean for our place in the cosmos? In this video, we'll explore the science, the theories, and the unanswered questions that make the Big Bang one of the most awe-inspiring topics in all of human knowledge. So, buckle up, we're about to take a journey back to the very beginning of everything. Picture this, a single point, unimaginably small and infinitely dense, containing all the energy, matter, and potential of the entire universe. Then, in an instant, it explodes outward, unleashing a firestorm of creation that would shape everything we know. This is the Big Bang, the moment our universe burst into existence 13.8 billion years ago. But what does that really mean? At its core, the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. From that initial singularity, a state of infinite density and temperature, the universe began to stretch, cool, and evolve, setting the stage for galaxies, stars, and planets to form over billions of years. So, how do we know this actually happened? One of the most compelling pieces of evidence is the cosmic microwave background radiation, often called the afterglow of the Big Bang. This faint glow, discovered in 1965, is essentially the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. It's like finding a fossilized footprint of the universe's infancy. Then there's the redshift of galaxies, observed by astronomers like Edwin Hubble. As galaxies move away from us, their light stretches into longer, redder wavelengths, showing that the universe is still expanding, a direct echo of that initial explosion. The Big Bang theory didn't just explain these observations, it completely transformed how we see the cosmos. Before this, many scientists believed the universe was static and eternal. But the Big Bang revealed a dynamic, evolving universe with a clear beginning. It gave us a framework to understand not just where we came from, but how the universe itself works. And yet, as groundbreaking as this theory is, it only tells part of the story. What happened in the moments immediately after the Big Bang? How did the universe go from a seething, chaotic soup of particles to the structured cosmos we see today? That's where things get even more fascinating. Now, let's zoom in even closer back to the very first moments after the Big Bang, a time so early that our current understanding of physics struggles to make sense of it. This is the Planck Epoch, a period lasting just 10 to the power of -43 seconds. To put that into perspective, it's a timescale so short that if you divided a single second into a trillion parts, the Planck Epoch would still be over 1 billion times shorter than one of those slivers. During this unimaginably brief moment, the universe was a seething, chaotic realm where gravity, space, and time as we know them didn't yet exist. Instead, everything was governed by quantum mechanics, a set of rules that operate on scales so tiny they defy our everyday intuition. It's like trying to describe a world where up is down, left is right, and time itself is fluid, utterly alien to anything we've ever experienced. But then, something extraordinary happened. Just fractions of a second after the Planck Epoch, the universe underwent a dramatic transformation known as cosmic inflation. Imagine blowing up a balloon at an incredible speed. so fast that every tiny wrinkle on its surface smooths out almost instantly. That's what inflation did to the early universe. In less than a blink of an eye, the cosmos expanded exponentially, stretching from a size smaller than an atom to something far larger than our entire observable universe today. This rapid expansion didn't just make the universe bigger, it also made it remarkably uniform. If you look at the cosmic microwave background, the afterglow of the Big Bang, you'll notice it's almost perfectly smooth with only tiny fluctuations. Inflation explains why. It stretched out any irregularities, leaving behind a nearly even distribution of energy and matter. But why does this matter? Without inflation, the universe might have remained a chaotic, clumpy mess, making it impossible for galaxies, stars, and planets to form. Instead, inflation set the stage for structure to emerge, creating the seeds for everything we see today. Those tiny fluctuations in the cosmic microwave background, they're like cosmic fingerprints, the faint echoes of quantum ripples from the early universe that eventually grew into the vast web of galaxies we observe now. It's a breathtaking reminder that even the smallest details in the cosmos can have monumental consequences. And yet, as incredible as inflation is, it's only the beginning of the story. Once the universe settled from its rapid expansion, it entered a new phase, one where the first particles began to take shape, setting the foundation for the building blocks of matter. But that's a tale for the next chapter of our cosmic journey. As the universe continued to cool and expand after inflation, it entered a phase that would set the stage for everything we know today. This was the era of the Quark-Gluon Plasma, a seething, primordial soup of particles so hot and dense that even atoms couldn't exist yet. Imagine a cosmic cauldron bubbling with quarks, the fundamental building blocks of matter, and gluons, the particles that bind them together. At this point, the universe was a chaotic, high-energy dance, with quarks and gluons constantly colliding, merging, and separating in a frenzy of activity. It's like trying to picture a crowded dance floor where everyone is moving at the speed of light, bumping into each other without ever forming lasting partnerships. But as the universe cooled further, something remarkable happened. Quarks began to combine, forming protons and neutrons, the very building blocks of atoms. This process, known as hadronization, was like the universe finally settling down after its wild, early party. Quarks, which had been free to roam, now paired up in groups of 3, creating the stable particles that would eventually make up the nuclei of atoms. It's a bit like how individual dancers might suddenly find their perfect partners, locking into place and creating something entirely new. Here's where things get even more intriguing. During this time, the universe wasn't just creating matter. It was also producing antimatter, the mirror image of matter with opposite properties. When matter and antimatter meet, they annihilate each other in a burst of energy. So, why didn't the universe destroy itself in a fiery collision of matter and antimatter? This is one of the greatest mysteries in physics. For reasons we still don't fully understand, there was a tiny imbalance, just one extra particle of matter for every billion particles of antimatter. That minuscule difference is the reason we exist today. Without it, the universe would have been left with nothing but energy, and galaxies, stars, and planets would never have formed. This imbalance, known as baryon asymmetry, is a puzzle that scientists are still trying to solve. Was it due to some fundamental law of physics we haven't discovered yet? Or was it the result of random fluctuations in the early universe? Whatever the cause, it's a reminder of how delicate and precise the conditions had to be for the cosmos to evolve as it did. It's like winning the cosmic lottery, a 1 in a billion chance that made all the difference. As the universe continued to cool, protons and neutrons began to come together, forming the first atomic nuclei. This marked the beginning of a new chapter in the story of the cosmos, one where the building blocks of matter were finally in place, ready to create the first atoms. But that's a story for the next phase of our journey, where we'll explore how the universe transitioned from a sea of particles to a place where light could finally shine through. As the universe cooled further, protons and neutrons began to come together in a process that would lay the foundation for all matter as we know it. This was the era of nucleosynthesis, a pivotal moment in cosmic history when the first atomic nuclei were forged. Picture this: just a few minutes after the Big Bang, the universe was still incredibly hot, but it had cooled enough for protons and neutrons to start combining. These particles, once free and chaotic, began to form stable pairs and triplets, creating the simplest atomic nuclei: hydrogen, helium, and a tiny bit of lithium. It's like watching the first bricks being laid for a cosmic structure that would eventually become everything we see today. But why these elements? Why not something heavier like carbon or oxygen? The answer lies in the conditions of the early universe. At this stage, the cosmos was still too hot and energetic for more complex elements to form. The intense heat and rapid expansion meant that only the lightest nuclei could stabilize. Hydrogen, with its single proton, was the simplest and most abundant. Helium, with 2 protons and 2 neutrons, came next, followed by trace amounts of lithium. These elements were the building blocks of the universe, but they were just the beginning. Heavier elements like carbon, oxygen, and iron would have to wait for the birth of stars billions of years later. To put this into perspective, let's look at the Sun. Even today, our star is primarily made up of hydrogen and helium, the very elements created during nucleosynthesis. In fact, about 75% of the Sun's mass is hydrogen, while helium makes up nearly 25%. The rest, just a tiny fraction of heavier elements. This composition is a direct echo of the early universe, a snapshot of that first few minutes when the simplest elements came into being. It's a reminder that the Sun, and every star like it, carries the legacy of nucleosynthesis within its core. This era didn't last long, just a few minutes, in fact. But in that brief window, the universe set the stage for everything that would follow. The hydrogen and helium created during nucleosynthesis became the fuel for the first stars, the raw material for galaxies, and the foundation for planets like Earth. Without this crucial step, the cosmos as we know it simply wouldn't exist. And yet, even as the universe began to take shape, it was about to enter a new phase, one of darkness and mystery. After nucleosynthesis, the cosmos continued to expand and cool, eventually reaching a point where light could no longer travel freely. This marked the beginning of the universe's dark ages, a time when the first stars had yet to ignite and the cosmos was shrouded in shadow. But that's a story for the next chapter of our cosmic journey. After the fiery chaos of nucleosynthesis, the universe entered a phase that might seem counterintuitive, a time of darkness. This period, known as the Cosmic Dark Ages, was a universe without stars, without galaxies, and without light as we know it. Picture a vast, endless fog, a thick, opaque haze of ionized gas that stretched across the cosmos. Light couldn't travel freely. It was constantly scattered and absorbed by this dense, hot plasma. For hundreds of millions of years, the universe was shrouded in this primordial gloom, a place where even the faintest glimmer of starlight had yet to pierce the veil. But why was the universe so dark? To understand this, we need to rewind a bit. After nucleosynthesis, the cosmos was still incredibly hot, filled with free electrons and atomic nuclei. These charged particles interacted with light, scattering it in every direction. Imagine trying to see through a dense, swirling fog. The light gets trapped, bouncing around endlessly. That's exactly what was happening in the early universe. Photons, the particles of light, couldn't travel far without being absorbed or deflected, leaving the cosmos in a state of near total obscurity. Then something extraordinary happened. As the universe continued to expand and cool, it reached a critical temperature around 3000 degrees Celsius. At this point, electrons, which had been zipping around freely, finally slowed down enough to be captured by atomic nuclei. This process, called recombination, marked the birth of the first neutral atoms, primarily hydrogen. Think of it like a cosmic game of musical chairs. As the universe cooled, the music slowed, and electrons found their seats, pairing up with protons to form stable atoms. With the formation of neutral atoms, the fog began to lift. Light, which had been trapped for so long, could now travel freely through space. This moment, known as the epoch of last scattering, is when the cosmic microwave background radiation we observe today was released. It's like the universe finally opened its eyes, allowing light to shine through for the first time. This ancient light, now stretched into microwaves by the expansion of the universe, is a snapshot of that pivotal moment, a faint echo of the cosmos stepping out of the shadows. The end of the cosmic dark ages didn't just bring light, it set the stage for the next great chapter in the universe's story. With the fog cleared, the cosmos became transparent, allowing gravity to work its magic. Tiny fluctuations in the density of matter left over from the early universe began to grow. These seeds of structure, imprinted during inflation, started to pull matter together, forming the first clumps of gas. Over millions of years, these clumps would grow denser and hotter, eventually igniting the first stars and lighting up the universe once more. This transition from darkness to light wasn't just a cosmic milestone, it was the beginning of everything we see today. The first stars, born from the ashes of the Dark Ages, would go on to forge heavier elements, seeding the universe with the building blocks of planets, life, and even us. But that's a story for another time, a story that begins with the dawn of starlight, piercing the darkness and heralding a new era of cosmic evolution. As the cosmic dark ages came to an end, the universe was poised for a dramatic transformation, one that would light up the cosmos for the very first time. This was the era of the first stars, known as population Roman 3 stars. Unlike the stars we see today, these ancient giants were made almost entirely of hydrogen and helium, the raw materials forged during nucleosynthesis. They were massive, hundreds of times heavier than our Sun, and burned with an intensity that's almost impossible to imagine. But their brilliance came at a cost. These stars lived fast and died young, their lives measured in mere millions of years rather than billions. What made these stars so special? For one, they were the first to ignite, breaking the darkness that had enveloped the universe for so long. Their intense radiation began to ionize the surrounding gas, stripping electrons from atoms and creating a hot, glowing plasma. This process, known as reionization, marked the end of the cosmic dark ages and the beginning of a new era, one where light could travel freely across the cosmos once more. It's like the universe had finally flipped a switch, illuminating the vast expanse of space with the glow of countless stars. But the impact of these first stars went far beyond just lighting up the universe. Their intense radiation and powerful stellar winds began to shape the cosmos, carving out bubbles of ionized gas and triggering the collapse of nearby clouds of matter. This set off a chain reaction, leading to the formation of even more stars and eventually the first galaxies. Gravity, the great architect of the universe, played a crucial role here. It pulled matter together, creating dense clumps of gas that collapsed under their own weight, igniting new stars and forming the building blocks of galaxies. These early galaxies were nothing like the majestic spirals and ellipticals we see today. They were small, chaotic, and filled with young, hot stars that burned brightly but didn't last long. Over time, these galaxies began to merge and grow, drawn together by gravity's relentless pull. This process of galactic evolution would eventually give rise to the vast cosmic structures we observe now, galaxies like our own Milky Way, each containing billions of stars and countless worlds. The first stars and galaxies didn't just light up the universe, they also seeded it with the elements necessary for life. When population Roman III stars reached the end of their short lives, they exploded in spectacular supernova, scattering heavier elements like carbon, oxygen, and iron across the cosmos. These elements became the building blocks for future generations of stars, planets, and ultimately life itself. It's a humbling thought. Every atom in your body, every molecule in the air you breathe, can trace its origins back to those ancient, long-vanished stars. As we look out into the night sky, we're seeing the legacy of those first stars and galaxies, a universe that's been shaped and illuminated by their light. But the story doesn't end here. The echoes of the Big Bang, imprinted in the cosmic microwave background, still ripple through the cosmos, carrying with them the secrets of the universe's earliest moments. And that's where our journey takes us next, into the faint whispers of the Big Bang itself, the clues that help us piece together the story of how it all began. Now, let's turn our attention to one of the most extraordinary discoveries in modern cosmology, the cosmic microwave background, or CMB. Think of it as a cosmic time capsule, a faint whisper of light that has traveled across the universe for nearly 13.8 billion years. This ancient radiation is the afterglow of the Big Bang itself, a snapshot of the universe when it was just 380,000 years old. To put that into perspective, if the universe's lifespan were a 24-hour day, the CMB would be a photograph taken just a few minutes after midnight. It's the oldest light we can see, and it holds the key to understanding the universe's earliest moments. So, what exactly is the CMB? Imagine the universe as a hot, dense soup of particles and energy in its infancy. At that time, light couldn't travel freely because it was constantly scattered by free electrons. But as the universe expanded and cooled, electrons combined with protons to form neutral atoms, allowing light to break free. This moment, known as recombination, marked the birth of the CMB. The light released during this epoch has been traveling through space ever since, stretched and cooled by the expansion of the universe into the faint microwave radiation we detect today. It's like finding a faded photograph of the universe as a newborn, revealing its earliest structure and composition. The CMB isn't just a uniform glow, it's a treasure trove of information. Tiny fluctuations in its temperature, just a few millionths of a degree, tell us about the seeds of structure in the early universe. These minute variations are the fingerprints of quantum fluctuations from the Big Bang, stretched by cosmic inflation into the patterns we observe today. They're the blueprint for everything we see: galaxies, stars, and even the vast cosmic web that connects the universe. Without these fluctuations, the cosmos would have remained a smooth, featureless void, and none of the structures we know would exist. Mapping the CMB has been one of the greatest achievements in astronomy. In the early 1990s, NASA COBE satellite made the first detailed measurements of this ancient light, confirming its existence and revealing its subtle variations. This discovery was so groundbreaking that it earned the COBE team the Nobel Prize in Physics. Later missions, like the Planck satellite, took this even further, producing incredibly precise maps of the CMB that have deepened our understanding of the universe's origins. These missions are like cosmic archaeologists, uncovering the faint traces of the Big Bang and piecing together the story of how it all began. But the CMB isn't just a relic of the past, it's also a window into the universe's future. By studying its patterns, scientists have been able to measure the universe's age, composition, and rate of expansion with remarkable accuracy. It's revealed that ordinary matter, the stuff we're made of, makes up less than 5% of the universe. The rest is a mysterious mix of dark matter and dark energy, two enigmatic forces that shape the cosmos in ways we're only beginning to understand. And that's where our journey takes us next, into the shadows of the universe, where dark matter and dark energy hold the keys to its ultimate fate. As we peer deeper into the cosmos, we uncover a startling truth. The universe we see, the stars, galaxies, and planets, is just the tip of the iceberg. In fact, the vast majority of the cosmos is made up of something we can't see, touch, or even fully understand. Enter dark matter and dark energy, the invisible forces that shape the very fabric of the universe. Together, they make up a staggering 95% of everything that exists, leaving the ordinary matter we're familiar with, the stuff of stars, planets, and even us, as just a tiny fraction of the cosmic pie. Let's start with dark matter, the universe's hidden scaffolding. Imagine a galaxy spinning through space. Based on the visible matter alone, stars, gas, and dust, it shouldn't hold together. The outer edges should fly apart like a merry-go-round spinning too fast, but they don't. Something invisible is holding galaxies together, something with enough gravitational pull to keep them intact. That something is dark matter. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet its presence is undeniable, revealed through its gravitational effects on the visible universe. Think of it as the cosmic glue, binding galaxies and galaxy clusters together in a vast, unseen web. But dark matter is just one piece of the puzzle. There's another, even more mysterious force at work: dark energy. While dark matter pulls the universe together, dark energy is doing the opposite, pushing it apart. In the late 1990s, astronomers made a shocking discovery. By observing distant supernova, they found that the universe isn't just expanding, it's expanding faster and faster over time. This accelerated expansion can't be explained by gravity alone. Instead, it's driven by dark energy, a repulsive force that makes up about 68% of the universe. Picture it as an invisible wind, relentlessly pushing galaxies away from each other, stretching the fabric of space itself. Together, dark matter and dark energy challenge everything we thought we knew about physics. They don't fit neatly into the standard model, the framework that describes the particles and forces we're familiar with. Instead, they hint at a deeper, more complex reality, one that we're only beginning to explore. For instance, what is dark matter made of? Is it a new kind of particle, something we've yet to detect? And what about dark energy? Is it a property of space itself, or does it arise from some unknown force? These questions aren't just academic, they're fundamental to understanding the universe's past, present, and future. The implications are profound. Without dark matter, galaxies wouldn't have formed, and the universe would be a very different place. Without dark energy, the cosmos might have collapsed back in on itself long ago. These invisible forces are the architects of the universe, shaping its structure and destiny in ways we're still trying to comprehend. And yet, despite their importance, they remain elusive, hiding in the shadows of our understanding. As we grapple with these mysteries, we're reminded of how much we still have to learn. The Big Bang gave us the universe, but it also left us with questions that push the boundaries of science. What sparked the initial expansion? What lies beyond the observable universe? And how do dark matter and dark energy fit into the grand cosmic story? These are the puzzles that drive astronomers and physicists to keep searching, to keep exploring, and to keep asking, what really happened at the beginning of everything? As we've journeyed through the story of the Big Bang, one thing becomes clear. While we've uncovered incredible insights about the universe's origins, there are still profound mysteries that defy our understanding. These unanswered questions aren't just gaps in our knowledge, they're windows into the deepest secrets of existence. What caused the initial singularity, that infinitely dense point from which everything emerged? What, if anything, existed before the Big Bang? And why does the universe seem so perfectly fine-tuned for life, as if every constant and law of physics were carefully calibrated to allow stars, planets, and even us to exist? Let's start with the singularity itself. The Big Bang theory describes the universe's rapid expansion from an unimaginably hot and dense state, but it doesn't explain what triggered that expansion or what the singularity actually was. Some scientists suggest that the singularity might not be a physical point at all, but rather a breakdown in our understanding of physics. At such extreme conditions, the laws of general relativity, which govern gravity and the large-scale structure of the universe, collide with the bizarre rules of quantum mechanics, which describe the behavior of particles on the smallest scales. To truly understand the singularity, we might need a theory of quantum gravity, a framework that unites these two pillars of physics. Theories like string theory and loop quantum gravity are attempts to bridge this gap, but so far they remain tantalizing possibilities rather than proven truths. Then there's the question of what came before the Big Bang. Was there a before at all? Some theories propose that our universe is just one in an endless cycle of expansions and contractions, a cosmic heartbeat that has been pulsing for eternity. Others suggest that the Big Bang was the result of a collision between two higher-dimensional branes in a multiverse, a vast, perhaps infinite, collection of parallel universes. In this view, our universe is just one bubble in a cosmic foam, each with its own unique laws of physics. While these ideas are speculative, they challenge us to think beyond the limits of our observable universe and consider the possibility of realities we can't yet imagine. Perhaps the most puzzling mystery of all is the fine-tuning of the universe. Why do the fundamental constants of nature, like the strength of gravity or the mass of an electron, have the precise values they do? If any of these constants were even slightly different, stars wouldn't form, atoms wouldn't hold together, and life as we know it would be impossible. Some scientists argue that this fine-tuning is evidence of a multiverse, where countless universes exist with different constants, and we just happen to live in one where the conditions are right for life. Others see it as a hint of something deeper, perhaps even a sign of a cosmic designer. Whatever the explanation, it's a question that forces us to confront the very nature of reality. These mysteries remind us that the Big Bang isn't just a story about the past, it's a doorway to questions that push the boundaries of human knowledge. What lies beyond the edge of our observable universe? Are there other dimensions we can't perceive? And could there be other universes, each with its own unique story? These aren't just scientific questions, they're philosophical ones, inviting us to ponder our place in the cosmos and the limits of what we can ever hope to understand. As we grapple with these questions, it's worth remembering that the Big Bang theory, while incredibly successful, isn't the only explanation for the universe's origins. In fact, there are alternative theories that challenge the traditional narrative, offering new perspectives on how everything began. And that's where our journey takes us next, into the realm of ideas that go beyond the Big Bang, exploring the possibilities that might reshape our understanding of the cosmos once again. While the Big Bang theory has become the cornerstone of modern cosmology, it's not the only idea scientists have proposed to explain the origins of the universe. In fact, there are several alternative theories that challenge the traditional narrative, each offering its own unique perspective on how everything began. These models don't just exist to stir debate, they're part of the scientific process, pushing us to question, refine, and sometimes even rethink our understanding of the cosmos. Let's take a closer look at some of these intriguing alternatives. One of the earliest challenges to the Big Bang was the steady-state theory. Proposed in the mid-20th century, this model suggests that the universe has no beginning or end. It's always existed and always will. Instead of a single explosive event, the steady-state theory posits that new matter is continuously created as the universe expands, maintaining a constant density over time. Imagine a river that never runs dry, constantly replenishing itself as it flows. This idea was appealing because it avoided the need for a singular starting point, but it faced a major hurdle, the discovery of the cosmic microwave background. The CMB's existence strongly supported the idea of a hot, dense beginning, making the steady-state theory difficult to reconcile with the evidence. While it's no longer widely accepted, the steady-state model played a crucial role in shaping the scientific conversation, reminding us that even the most established ideas can be questioned. Another fascinating alternative is the cyclic model, which proposes that the universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang wasn't the beginning of everything, it was just one in a series of cosmic rebirths. Picture a cosmic heartbeat with the universe expanding, cooling, and then collapsing back into a dense state, only to explode outward again in a new Big Bang. This idea addresses some of the Big Bang's unanswered questions, like what came before the initial singularity. However, cyclic models face their own challenges, particularly in explaining how the universe could transition smoothly from contraction to expansion without violating the laws of physics. Despite these hurdles, the concept of an eternal, cyclical universe continues to captivate scientists and philosophers alike. Then there's the Ecparotic universe, a theory rooted in string theory. This model suggests that our universe was born from the collision of two higher-dimensional membranes of energy in a multiverse. Think of it like two sheets of paper slamming together, creating a burst of energy that sparked the Big Bang. The Ecparotic model offers an elegant solution to some of the Big Bang's puzzles, such as the uniformity of the cosmic microwave background. But like other alternatives, it's still speculative, relying on ideas that are difficult to test with current technology. What's remarkable about these theories isn't just their creativity, it's the way they highlight the scientific process. Science isn't about finding a single, unchanging truth. It's about asking questions, testing ideas, and refining our understanding over time. Take, for example, the ongoing debate over the universe's expansion rate. Measurements from different methods like supernova and the cosmic microwave background sometimes produce conflicting results. This discrepancy, known as the Hubble tension, has sparked intense discussion and even led some to question whether our current models of cosmology need to be revised. It's a reminder that science is a living, evolving field, always open to new ideas and discoveries. As we explore these alternative theories, it's clear that the story of the universe's origins is far from settled. Each model offers a unique lens through which to view the cosmos, challenging us to think beyond the familiar and consider possibilities we might never have imagined. But to truly test these ideas, we need more than just imagination, we need cutting-edge technology. And that's where our journey takes us next, into the tools and techniques that allow us to peer deeper into the universe's past than ever before. To uncover the secrets of the Big Bang, we rely on some of the most advanced tools humanity has ever created. These instruments act as time machines, allowing us to peer billions of years into the past and witness the universe in its infancy. At the forefront of this cosmic detective work are telescopes both on Earth and in space. Ground-based observatories like the Atacama Large Millimeter Array in Chile capture faint signals from distant galaxies, while space-based telescopes such as the Webb Space Telescope provide crystal-clear views of the cosmos, free from the distortion of Earth's atmosphere. But the crown jewel of modern astronomy is the James Webb Space Telescope, or JWST. Launched in 2021, JWST is designed to see farther and more clearly than any telescope before it. Its infrared vision allows it to pierce through cosmic dust and observe the first galaxies that formed after the Big Bang, giving us a front-row seat to the universe's earliest chapters. But telescopes aren't the only tools in our cosmic toolkit. To understand the extreme conditions of the early universe, scientists turn to particle accelerators like the Large Hadron Collider, or LHC. By smashing particles together at nearly the speed of light, the LHC recreates the intense energy and density of the universe just moments after the Big Bang. These experiments help us test theories about how matter and energy behaved in those first fractions of a second, offering clues about the fundamental forces that shaped the cosmos. It's like running a cosmic simulation in a lab, giving us a glimpse into the universe's most extreme moments. Another critical tool in our quest to understand the Big Bang is computer simulations. Using supercomputers, scientists can model the evolution of the universe from its earliest moments to the present day. These simulations take into account everything from the laws of physics to the distribution of dark matter, allowing researchers to test theories and make predictions about how the cosmos evolved. For example, simulations have helped us understand how tiny fluctuations in the early universe grew into the vast cosmic web of galaxies we see today. It's like building a virtual universe where we can tweak the parameters and see how everything unfolds. Together, these tools, telescopes, particle accelerators, and simulations give us a multifaceted view of the Big Bang and its aftermath. They allow us to piece together the story of how the universe began, how it evolved, and how it continues to change. But as we gather more data and refine our models, we're also confronted with deeper questions about the nature of reality. What does it mean to observe the universe's origins, and how do these discoveries shape our understanding of our place in the cosmos? These aren't just scientific questions, they're philosophical ones, inviting us to reflect on the profound mysteries that lie at the heart of existence. As we continue to push the boundaries of technology and knowledge, we're reminded that the story of the Big Bang isn't just about the past, it's about the future. Every discovery, every new piece of data brings us closer to understanding the universe's origins and perhaps our own. And with each step forward, we're not just uncovering the secrets of the cosmos, we're also uncovering the potential of human curiosity and ingenuity to explore the unknown. The Big Bang isn't just a scientific theory, it's a profound idea that challenges us to think about the very nature of existence. What does it mean that everything we know, from the stars above to the ground beneath our feet, emerged from a single, unimaginably dense point? For centuries, philosophers and scientists alike have grappled with questions about the origins of the universe and our place within it. The Big Bang doesn't just answer some of these questions, it also raises new ones, inviting us to reflect on the deeper meaning of life and the cosmos. Take, for example, the concept of time. Before the Big Bang, time as we understand it didn't exist. There was no before, no after, just a singularity where the rules of physics break down. This idea challenges our everyday understanding of reality. As physicist Stephen Hawking once said, the universe doesn't have a boundary in time, just as the Earth doesn't have an edge. It's a thought that stretches the limits of our imagination, forcing us to reconsider what we think we know about beginnings and endings. But the Big Bang isn't just a scientific puzzle, it's also a source of wonder and inspiration. For many, it bridges the gap between science and spirituality, offering a glimpse into the profound interconnectedness of all things. Carl Sagan famously described the cosmos as all that is, or ever was, or ever will be, a poetic reminder that we are part of something much larger than ourselves. This sense of awe isn't just reserved for scientists, it's something anyone can feel when they look up at the night sky and realize that every atom in their body was forged in the hearts of ancient stars. The Big Bang also raises questions about purpose and meaning. If the universe began as a random, chaotic event, does that mean life is ultimately without purpose? Or does the sheer improbability of our existence, the precise conditions that allowed stars, planets, and life to form, suggest something more? Philosophers like Albert Camus have wrestled with these ideas, exploring the tension between the universe's apparent indifference and humanity's search for meaning. The Big Bang doesn't provide easy answers, but it invites us to ask the questions that define what it means to be human. And then there's the question of our place in the cosmos. The universe is vast, almost incomprehensibly so, with billions of galaxies stretching across billions of light years. In the face of such enormity, it's easy to feel small, even insignificant. But as astronomer Neil deGrasse Tyson reminds us, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us. The atoms that make up our bodies were once part of stars, and the energy that powers our thoughts is a direct legacy of the Big Bang. In that sense, we are not just observers of the universe, we are its living, breathing expression. These philosophical reflections don't just deepen our understanding of the Big Bang, they also connect us to the broader human experience. Whether through science, art, or spirituality, the story of the universe's origins resonates with something deep within us, a curiosity about where we came from and where we're going. It's a story that transcends disciplines, uniting us in our shared quest for knowledge and meaning. As we ponder these big questions, it's worth remembering that the story of the Big Bang is still being written. Every discovery, every new piece of data brings us closer to understanding the universe's origins and perhaps our own, but the journey doesn't end here. In the next chapter of our cosmic exploration, we'll look to the future of cosmology, where cutting-edge technology and bold new ideas promise to reveal even more about the mysteries of the universe. What lies ahead? The answers may surprise us and inspire us to keep asking the questions that drive humanity forward. As we stand on the brink of a new era in cosmology, the tools and technologies at our disposal are more powerful than ever before. The future of understanding the universe is not just about refining what we already know. It's about uncovering entirely new layers of reality. One of the most exciting developments on the horizon is the Vera Rubin Observatory, set to begin operations in the next few years. This groundbreaking facility, perched high in the Chilean Andes, will conduct the Legacy Survey of Space and Time, or LSST. Over the course of a decade, it will map the entire visible sky in unprecedented detail, capturing images of billions of galaxies and tracking the movements of countless celestial objects. Imagine having a time-lapse video of the universe, revealing how galaxies evolve, how dark matter shapes their growth, and even how the cosmos itself is expanding. The Vera Rubin Observatory isn't just a telescope, it's a cosmic census, offering a wealth of data that could transform our understanding of the universe's structure and history. But the Vera Rubin Observatory is just the beginning. Another frontier in cosmology is the search for gravitational waves, ripples in the fabric of space-time caused by cataclysmic events like the collision of black holes or neutron stars. Since their first detection in 2015, gravitational waves have opened a new window into the universe, allowing us to listen to phenomena we could never see with traditional telescopes. Future missions like the Laser Interferometer Space Antenna, or LISA, aim to take this even further. LISA, a space-based observatory, will detect gravitational waves at lower frequencies, potentially revealing the echoes of the universe's earliest moments. It's like tuning into a cosmic symphony where each note tells a story about the birth and evolution of the cosmos. Advancements in quantum physics are also poised to revolutionize cosmology. One of the most tantalizing possibilities is the discovery of new particles that could shed light on the nature of dark matter and dark energy. For decades, these mysterious forces have eluded direct detection, but experiments like those at the Large Hadron Collider and future facilities like the Deep Underground Neutrino Experiment, or DUNE, are pushing the boundaries of what we can observe. Imagine finding a particle that doesn't fit into the standard model of physics, a discovery that could rewrite the rules of the universe and unlock secrets about its origins. These experiments aren't just about answering old questions, they're about uncovering entirely new ones, challenging us to rethink our understanding of reality. Artificial intelligence is another game changer in the field of cosmology. With the sheer volume of data being collected by telescopes and experiments, traditional methods of analysis are no longer sufficient. AI algorithms can sift through this data at incredible speeds, identifying patterns and anomalies that might otherwise go unnoticed. For example, AI is already being used to classify galaxies, predict the behavior of cosmic structures, and even simulate the early universe. It's like having a tireless assistant that can process information faster and more accurately than any human, helping us uncover insights that were once hidden in the noise. As we look to the future, it's clear that the journey to understand the universe is far from over. From the Vera Rubin Observatory's sweeping surveys to the hunt for gravitational waves and the quest for new particles, each new discovery brings us closer to unraveling the mysteries of the Big Bang. But perhaps the most exciting part of this journey is the unknown, the questions we haven't even thought to ask yet. What lies beyond the edge of our observable universe? Are there other dimensions waiting to be discovered? And what new technologies will emerge to help us explore these frontiers? This journey from the Big Bang to the cutting edge of cosmology reminds us that science is a never-ending quest for knowledge. It's a story of curiosity, collaboration, and the relentless pursuit of understanding. And as we prepare to conclude our exploration, it's worth reflecting on how far we've come and how much further we have yet to go. The universe is vast, mysterious, and full of surprises, and the next chapter in our cosmic story promises to be as thrilling as the last. As we reach the end of our journey through the cosmos, let's take a moment to reflect on the incredible story we've uncovered. From the unimaginable singularity of the Big Bang to the vast, intricate web of galaxies we see today, the universe has revealed itself to be a place of both breathtaking beauty and profound mystery. We've explored how the universe burst into existence 13.8 billion years ago, how it expanded and cooled, and how the first stars and galaxies ignited, lighting up the darkness. We've marveled at the cosmic microwave background, the faint echo of the Big Bang itself, and grappled with the enigmatic forces of dark matter and dark energy that shape the cosmos. And yet, for all we've learned, the universe still holds secrets that challenge our understanding and ignite our curiosity. The Big Bang isn't just a scientific theory. It's a story about beginnings, about the origins of everything we know and everything we are. It's a reminder that the atoms in our bodies, the air we breathe, and the stars above us are all connected by a shared history that stretches back to the very first moments of existence. As Carl Sagan famously said, "We are made of star stuff." Every element in the universe, from the simplest hydrogen atom to the complex molecules that make up life, was forged in the hearts of stars and scattered across the cosmos by the explosive power of supernova. In that sense, we are not just observers of the universe, we are its living, breathing expression. But the story of the Big Bang is also a story of questions. What sparked the initial expansion? What lies beyond the edge of our observable universe? And what role do dark matter and dark energy play in shaping the cosmos? These mysteries remind us that science is a journey, not a destination. Every discovery opens new doors, inviting us to explore further, to ask deeper questions, and to push the boundaries of what we think we know. It's a journey that requires not just curiosity and creativity, but also humility, a recognition that the universe is far more complex and wondrous than we can ever fully comprehend. As we close this chapter, I want to leave you with a thought. The universe is vast, ancient, and filled with mysteries, but it's also a place of infinite possibility. Every time we look up at the night sky, we're reminded of how much there is to discover, how much there is to learn, and how much there is to wonder about. Whether you're a seasoned astronomer or someone who's just beginning to explore the cosmos, the story of the Big Bang is a reminder that we're all part of something extraordinary. So, what do you think? What fascinates you most about the universe's origins? Share your thoughts in the comments below. I'd love to hear your perspective. And if you enjoyed this journey through the cosmos, don't forget to subscribe for more mind-expanding content. Together, let's keep exploring the mysteries of the universe, one discovery at a time. After all, as the great physicist Richard Feynman once said, the most important thing is not to stop questioning. Curiosity has its own reason for existing. So let's keep asking questions, keep seeking answers, and keep marveling at the wonders of the cosmos. The universe is